Hello everyone, my name is Adam Harris and I did my final project on rotating Rayleigh-Bénard convection. Today I'll demonstrate how rotation inhibits the onset of convection. To start, let's review what we know about convection. Convection is motion induced in a fluid by temperature differentials. Changes in temperature cause changes in density, which give rise to buoyancy forces, which is why hot fluid rises and cold fluid sinks. The Grashof number is a measure of buoyancy forces to viscous forces. The Prandtl number is a measure of momentum and thermal diffusivity, and the Rayleigh number is the product of the two. Properties of a specific fluid result in that fluid having a critical value of the Rayleigh number. For values of the Rayleigh number above its critical value, the fluid is sensitive to temperature perturbations, while for values of the Rayleigh number below its critical value, no convection occurs. As such, the Rayleigh number acts as a governor to convection. For our setup, we can imagine fluid in a tank where the tank itself is rotating with constant angular velocity, and we are observing through a camera mounted to the tank. In the rotating frame, we now have two new parameters to consider: the Ekman number, which is inversely proportional to the Coriolis forces, and the Taylor number, which is proportional to the centrifugal forces. Both of these parameters are ratios to viscous forces. Here, we have the visualization of two simulations run with Quick, which uses spectral methods to numerically solve the Navier-Stokes equations, much like what we've seen with data lists during lectures. We have the rotating case on the left and the non-rotating case on the right. Visualized is the z-directional vorticity in two plane layers of fluid, where blue represents positive vorticity and counterclockwise motion, and yellow represents negative vorticity and clockwise motion. Both simulations were run with isothermal and stress-free boundary conditions, a Prandtl number at unity, and a Rayleigh number of 2 times the critical value. The rotating case was run at an Ekman number of 10 to the minus 6. There are some fundamental differences here. While there is vorticity throughout the fluid on the right, it's nothing like what we see on the left, where we have clear vortex formation and vortex interaction. Also, notice the massive difference between the critical Rayleigh numbers of the two cases. The rotating critical Rayleigh number is on the order of hundreds of millions, while the non-rotating case is only on the order of hundreds. The question then is, what is the reason for this massive difference? We know that in a stationary frame with isothermal and stress-free boundary conditions that the critical wave and Rayleigh numbers are analytically found and constant. However, in our rotating frame, the critical wave and Rayleigh numbers scale asymptotically with the non-dimensional rotation parameters. The Ekman number is a measure of the Coriolis forces. Kc goes as the Ekman number to the minus third, and RAC goes as the Ekman number to the minus 4/3. And for the Taylor number, being a measure of the centrifugal forces, Kc goes as the Taylor number to the 1/6, and RAC goes as the Taylor number to the 2/3. Plotted here are the asymptotic behaviors of the critical wave number in blue and the critical Rayleigh number in red, for the Ekman number on top and Taylor on bottom. Here, we clearly see that the critical wave and Rayleigh numbers blow up in the limit that the Ekman number goes to 0 and the Taylor number goes to infinity, which corresponds to increasing Coriolis and centrifugal forces respectively. If we think of the critical Rayleigh number as a barrier to entry for convection, then increasing the Rayleigh number due to increasing rotational forces tells us that rotation inhibits the onset of convection. Rotating fluids are subject to Coriolis and centrifugal force, and as these forces increase, so does the critical Rayleigh number. Larger rotational forces make it more difficult for a fluid to begin convecting, and depending on properties of a fluid, for large enough Coriolis and centrifugal forces, convection is prevented entirely. Plotted here on a logarithmic scale are calculations of the critical Rayleigh number and critical wave number, as well as outputs from Quick of the average kinetic energy and average Reynolds number for Ekman cases run at 2 times the critical Rayleigh number. The Ekman number is the horizontal axis for all of these. Here we can see that the kinetic energy and the Reynolds number increase dramatically in the limit that the Ekman number goes to 0, and thinking of the critical Rayleigh number as a barrier to entry for convection, this data is showing that larger barriers, once broken, result in more energetic and more turbulent flows. Further research would drive us to consider the Nusselt number, which is the ratio of convective to conductive heat transfer in a fluid. H is the convective heat transfer coefficient, L is a typical length scale, and K is the thermal conductivity. It was observed during these simulations that the Nusselt number approaches a constant value in the limit that the Ekman number goes to 0, and suggests that the dynamics approach an asymptotic and self-similar state. This is unlike the behavior of every other quantity observed in this project, and is certainly worth further investigation. Thank you very much.